Okay, so now let's take a look at how it is that a derivative will actually affect the shape of a graph. And then we'll focus on something more specific, basically increasing and decreasing. Okay, so if we look here, and let's say I have a graph like this one here in number 1. Okay, and what I see is that going from A to B. Okay, so as I go from A to B, the function is itself increasing. And let's take a look at the slopes of the tangent lines. So if we look at the slopes of the tangent lines, the slopes of those tangent lines, they end up being positive. Okay, so the whole idea, like as the graph, as we increase in values, the slopes of the tangent lines are going to be positive. Then we already know, we've seen already that at our peaks and our valleys, okay, what we have is that the derivative is equal to 0. Okay, so that's really kind of handy too. Then you can see that on our decreasing interval from B to C, that we have negative slopes of our tangent lines, and then we'll have positive slopes of the tangent lines going from C to D. Okay, so basically, if I look at this, right, I can see that from A to B, I have my slopes are increasing. Okay, and I also know that from C to D, that my slopes are also increasing, and so the function's increasing as well. Notice that I didn't include A, B, C, or D. Okay, I could technically actually include D if I wanted to, and I could include A if I wanted to as well, because it turns out, well, you know what? Actually, I'm not going to include those in. All right, and that's because at B and C in particular, what we have is the derivative is equal to 0. It's not actually positive, and so consequently, it's neither increasing nor decreasing. Then whereas it decreasing, we know that this is from B to C. Okay, and what we see is that we get here that the slope of the tangent line, or the derivative, is positive when we have increasing function, and the derivative is negative when the function is decreasing. Okay, right? And so basically that's the answer to this. What can we say about the slopes of the tangent lines over these intervals? All right, so let's actually put this into more concrete terms or more mathematical terms. Okay, so we'll have this increasing decreasing test. If f prime of x is greater than 0 on an interval, then f of x is increasing on that interval. There it is. F prime of x is positive, f of x is increasing on the interval. If f prime of x is less than 0 on the interval, then f of x is decreasing on that interval. And there we go. That's the second part. Okay, so basically that's how we determine whether or not a function's increasing or decreasing. All right, and then what we're going to do is we're going to then use critical numbers, because if you notice, if I go back to my equation, right, at A, right, that's our endpoint, D is our endpoint, and then we have critical numbers at B and C. So if f is continuous, okay, then the only time that it's going to be changing from increasing to decreasing is when the slope becomes 0. Okay, basically at those critical numbers. Okay, so that's our first derivative test. So suppose that C is a critical number of a continuous function f. If f prime changes from positive to negative at C, f has a local maximum at C. Oh, wait, great, that's great, because that tells me how do I figure out when do I have a local maximum? It's when it goes from positive to negative, right? Let's take a look at this, right? If we see A to B, it's positive here, and then it's negative from B to C, so we have a max. Then we go from negative to positive, and that's going to be our min. So that's how we know that we have the local minimums and maximums. That kind of finishes out that minimum and maximum kind of idea. All right? If f prime does not change sign at C, then f doesn't have a local minimum, maximum, or a local minimum at C. Okay? So like, for example, in that case of like f of x equals x cubed that we saw before, what you got there was it's positive. It was increasing before our derivative, and it was increasing after our derivative, or after the derivative was equal to 0. So consequently, we ended up with neither a local minimum or a maximum. So just kind of review that. If f prime changes from positive to negative at C, f has a local maximum at C. If f prime changes from negative to positive at C, f has a local minimum at C. And if f prime does not change sign at C, then f doesn't have a local maximum or a local minimum at C. So let's make a consideration. Let's consider the function f of x equals 2x cubed plus 3x squared minus 36x. Let's find the intervals on which f is increasing. Okay, so the first thing that I actually want to do is I want to find my critical values. Okay, so I'll find my critical values, or critical numbers, excuse me, find my critical numbers. So if you remember, that's where f prime of x is equal to 0. So we'll have f prime of x equal to 6x squared plus 6x minus 36, okay, which is equal to 6 times x squared plus x minus 6, okay? And so this is going to be 6 times x, x plus 3 times x minus 2, and we'll set that equal to 0, okay? And so that means that x is going to equal negative 3, and x will equal 2. Those are our critical numbers. Then what I'm going to do is I'm actually going to draw a little line, and I'm going to do some testing, okay? I'm going to do some testing. And so I'll start out, here's negative 3, here's 2, okay? By the way, we should get that since this is a polynomial, it's differentiable everywhere, so we don't have those other problematic critical numbers, all right? So what I'll do first is I'll choose a value less than negative 3. Say I'll take negative 4, okay? So we find f of negative 4, okay? And all I really need to notice is I need to notice that this, in fact, is going to end up being, f prime of negative 4. Sorry, f prime of negative 4. And when I plug that in to f prime, what I get is I get 6 times a negative number times a negative number. So that ends up being positive. So f prime of negative 4. And I want to emphasize again, I'm taking the derivative. I'm finding the value of the derivative. So the derivative is positive before negative 3. Let's put in 0. So we'll find f prime of 0. And so that's going to end up being 6, again, times 0 plus 3. That's positive. So I actually just write my values plus, minus. So this is going to end up being negative. Okay. And then let's try 2. So we'll choose f prime of 3, a value bigger than 2. And so that gives me positive, right? Positive and positive. So they're all positive. When I multiply them all together, I'm going to get a positive. So that's going to be positive. Okay. So what we get there is, so f is increasing from negative infinity to negative 3, not at 3, by the way, union, okay, 2 to infinity, and decreasing from negative 3 to 2, okay? So what do we do there? Well, basically, in order to determine where our function was increasing or decreasing, we took the derivative, set it equal to 0 to find our critical numbers, okay? Those places where it's actually going to change from increasing to decreasing, okay? Then, once I found those critical numbers, I basically kind of created a graphical representation in order to kind of understand where it's going to be negative and positive, right? And I tested on either side of the critical numbers to determine if the derivative, right, okay, remember that's the derivative, if the derivative is positive or negative at those values, okay? So just be very careful. Increasing and decreasing, we're going to check on the derivative, right? Once I did that, okay, that told me where it was going to be increasing and where it was going to be decreasing, okay? Now, find the local minimum and maximum and minimum values. Well, all I've got to do is I've got to notice, I've got f of negative 3, okay, which is going to equal f of negative 3 is going to end up giving me 945. Excuse me, 945. Sorry. Okay. And we know that that's going to be a maximum because we've got plus, okay, that'll be a local maximum, and then to minus. So the derivative shifts from positive to negative around negative 3. So that means that the slope goes up, right? And then the slope goes down. So that means is the local maximum. On the other hand, f of 2, okay, which ends up equaling negative 44, it's going to be a local minimum because we've got the slope going down, and then the slope will go back up, okay, is the local minimum. Okay? All right. And so that's the entirety of showing where a function is in fact increasing And how do we find whether or not something's a local minimum or maximum? Okay, what you need to do here is you need to go in and you need to utilize both of these tests. You need to understand these tests. You might even want to like memorize what the tests are. Okay, until it becomes really clear what it is that you're doing. The first one, increasing, decreasing, not so hard. If the derivative is positive, it's increasing. If the derivative is negative, the function's decreasing on that interval. Okay, the second one, right, we want to get if the derivative goes from positive to negative, okay, then that means we must be at a max. Positive to negative, we must be at max. If it goes from negative to positive, we must be at a minimum. Okay, and if f prime does not change at c, then f doesn't have a local maximum or minimum at c. Okay, definitely something that you want to make sure that you study. And that completes our lesson on increasing, decreasing, and the local minimum and maximum values.